Hello, I am Thomas Morris. I am a PhD student at Yale and also a researcher at Brookhaven Lab. I work mostly on CMB experiments like ACT and SO and that sort of thing, but I like to do different projects in millimeter astronomy generally. So this talk is about Maria. Maria is a simulator for radio and microwave telescopes that I've developed and has been used for some AtLAST stuff. And I just wanted to sort of go through the things it does, how it approaches simulating different things, and mostly just as an introduction to what Jonas will be talking about, which is a new method of denoising observations using simulations. Um, so I don't have to tell you why a good simulator is important because there's just tons of different reasons, but it informs what you do before you build the telescope. It can help you decide which parameters you need to optimize, what the trade-offs are, because there's just many different ways to build a telescope. It can help with um, where you want to build it. So depending on what you want to observe, it might be advantageous to build it in some location versus another location. And if you're going to be asking for a lot of money to build this telescope, you should be able to say, I will be able to see this thing with this much observation. It will be this productive. And that's really only a question you can answer with simulations because it just depends on so many things. And then after you build the telescope, it's can help you figure out what sources you can look at, how much observation time it'll need. Um, and it can help you develop denoising and map making algorithms, which I'm especially interested in. And we'll hear a bit more about Jonas's denoising algorithm later on. So Maria is meant to be very straightforward and easy to use. So getting into it should be pretty simple. It's a Python package. You can just pip install it. And the minimal example on the right is, 8 lines of code, and it'll spit out a map of an example observation of a cluster. So if you just give it a cluster and you want to observe it with AtLAST, then it'll just do that pretty simply. So here, what's going on is you import the package in your input map. It just loads it from a FITS file that you have. The planner will say, I'd like to look at this map from this location, and I'd like it to be at least so far above the horizon. You can also specify I want it to be at this azimuth range or this range of hours during the day. And it'll figure out exactly when it can observe that, and it'll put that into a plan. And it'll generate a bunch of plans based off of the total amount of integration time you want. And then it'll just do a comprehensive simulation with the plan. It'll be atmosphere, there'll be instrument noise, it'll sample the map, it'll do all the computations to figure out how many picowatts are hitting each detector. And then it'll just spit that into a TOD as a time-ordered data object. And then you can plug that into a mapper, and it'll make you a map, and you'll figure out how your simulation did. And there's lots of documentation. There's lots of documentation on the website, and it's getting better all the time. But the idea is that you can also make this as comprehensive and as complicated as you want. Um, I've been giving it a lot of flexibility so that in principle, you should be able to simulate any single dish observatory. Once in a while, I'll get something that it can't do, and then I just implement that. So at this point, there's really very few things that it can't do. Um, and even for very large amounts of detectors like AtLAST, or for something with tens of thousands of detectors, hundreds of thousands of detectors, um, it uses both parallelized computation, which evaluates things in parallel, but it doesn't hold everything in memory at the same time. It uses this Python package called dask, which will save all the data to disk and only recall it when you need it, so it doesn't hog up all your RAM and crash your laptop. So the point is that you can do fairly bulky simulations on even just your laptop to try them out. Um, the main feature of Maria and what is most most derived from my work on CMB observations is the atmospheric simulations. Atmosphere is the dominant source for these wavelengths, for these time scales and these spatial scales. And so modeling them well and modeling them accurately is going to be the deciding factor of how good your simulation is and what scales you can recover. For large telescopes like AtLAST with a big aperture, the effect of the near field beams is very important. This figure on the right shows both the physical size of the beam on the left and the angular size of the beam on the right. And this gray strip between about 10 meters and a kilometer is where most of the atmosphere is located. And at that point, for AtLAST or for any radio telescope, pretty much, there'll be a huge near field beam because it's kind of blurry. It's like trying to look at something right in front of your nose. Every detector will just see the same thing, and the atmosphere will be very correlated between all the detectors. And so capturing that for doing accurate forecasting for instruments like this is extremely important. And so Maria will model the atmosphere not in 3 dimensions. In 3 dimensions, for a lot of practical reasons, it's pretty impossible to do beams. And so CMB simulators like Toast will just not bother with the beams at all. And that's usually a pretty good approximation for large field of view stuff and for relatively small apertures on the order of, a few meters. But as you get to the tens of meters or 100 meters, like you have for Mustang, this effect becomes very important. So we can model this as a 2 dimensional flat sheet, which is a common approximation, but we do many of them because that will help you take into account this beam thing, which acts differently in different layers of the atmosphere. Um, the spectrum is also very important because the atmosphere emits not as a constant black body or Rayleigh Jean source, but it has all these spiky spectral lines based off of the different molecular species in the atmosphere. And so Maria, to get this perfectly right, will exactly model the output. So it's as if you simulated the spectrum for every single detector sample and then figured out the total loading from that spectrum. It does everything explicitly to make sure that it's correct. And so as elevation changes, as PWV changes, as temperature changes, and as the altitude of the site changes, the spectrum changes in unpredictable ways. And so we just explicitly compute them, but using some clever interpolation, so you're not actually having to compute it every time. We also model path delay fluctuations exactly. And so future path of development is going to be to develop interferometric observations. And yeah, that'll be interesting. We also care about the atmospheric transmission on the bottom here, because if you have some source with a lot of loading, like like you're looking at the sun or you're looking at the CMB, there will be the fluctuations might come from variable transmission instead of variable emission. So just taking into account all of these different factors of the atmosphere is important. We also do a pretty comprehensive weather model. So using ERA 5, which is the European reanalysis data set, I have day averaged, year averaged, vertical atmospheric profiles for a lot of different sites, basically every site in the world where there is a radio telescope of note. And so Maria will just explicitly compute the atmospheric parameters and the fluctuation properties from this atmospheric profile. And so basically, wherever your telescope is, Maria can simulate it, and you don't have to rely on averaged atmospheric spectra. It will generate them. So there's a lot of use cases for Maria. You can see science forecasting of clusters. So Luca wrote a great paper about this using Maria. It can do time evolving sources like transient sources or solar physics, like Matt's did in his paper. You can observe polarized sources like this. I can generate this patch of CMB and I can scan over it with my telescope, and I can see how that picks up the polarized signal and how it maps it. There's really anything you can represent as a map or as a heel pix map can be an input to this. So there's really no limit to this amounts of sources you can simulate observations of. So let's say that I want to develop a mapping algorithm, and I want to take this snapshot of the Crab Nebula, and I want to observe it and figure out how to design my mapmaker to best reconstruct the picture of the thing. So a lot of mapmakers will solve the mapmaking equation here. E is the pointing matrix, N is the noise covariance matrix. So if D is a vector of all the samples, if I have N detectors and T timestamps, then I have NT data samples. So this is an NT by NT matrix. And so big data telescopes like AtLAST would have, billions or trillions of data points. And so a billion by a billion noise matrix is not feasible. And inverting that is extra not feasible. So if I want to solve this equation, I have to get clever about how I approximate the inverse of the noise covariance matrix. This is more of an art than a science, and a lot of different observatories do this differently. But if I'm trying to observe something and I want to design my algorithm to do that, then I had better have a good way of testing it. And so I can make a pretty simple one where I assume that the noise is stationary, which means that it's diagonal in Fourier space. And that's a simple way to do it. But if I want to test how well that assumption does on this observation, Maria is the only way I can do that. And so I make an observation with uh, a telescope that I designed in Maria. It has a field of view of 6 arc minutes. It has about 1,200 detectors. It's observing at 150 gigahertz. And I simulated a 20-minute observation. Just about 20 minutes, yeah. And so on the left here, you can see the time streams from the individual components. So the atmosphere fluctuates by many Kelvin, and the map fluctuates by less than a millikelvin. And the noise is also around a millikelvin. On the right, you can see the power spectra, and you can see how the different sources are relatively scaled with respect to each other. So then I put them into my mapper. I tried just removing the common mode, filtering it, and binning it. And then I get this guy in the middle who has a lot of kind of splotchy aliasing from the mapper. But it seems that my maximum likelihood mapper did a bit better. But you can see that there is this sort of large scale loss of power, which is a generic thing that happens with maximum likelihood mappers. But if I wanted to try to minimize this and try to say I'd like to recover large scales of this nebula, then I would iterate my mapper and I would use Maria to figure out, well, if I design my telescope this way and I use this mapper on that to observe that thing, then I can tune this pretty well. So we have a lot of plans for future development. I'm interested in modeling spectrographic observations because we do compute the atmospheric spectrum at a very uh, high resolution, and so it should be possible to sort of have pretty good kilohertz resolution of celestial sources. Um, so that's in development. I'd like to do interferometers. So there is, for interferometers, the atmosphere as a noise source, but it's not typically emission that gets averaged down by the interferometry. But there is a half delay fluctuation. So um, it's just a completely different kind of noise. But in principle, that is already generated by Maria. And so it's just a matter of specifying ALMA and, for example, and figuring out how to propagate all that noise into the signal. Um, there is polarized atmospheric noise. There's a lot of good papers about this, a lot of SPT stuff. And so that's an important noise source for CMB experiments and also for just anybody doing an observation of a polarized celestial source. Um, we'd like to run it on GPUs. Right now, it's all just CPU, but there's a lot of stuff that's done in parallel, and most of the stuff under the hood is just really big matrix multiplication. And so you can imagine that a GPU might speed that up quite a bit, but it's usually pretty fast. I mean, this stretch of time order data in particular for 1,200 detectors took about 10 seconds to simulate. So it's not really most simulations can be done on a laptop with not a very good processor. Um, and yeah, we're also developing better mapping algorithms, which this comprehensive simulation gives us a unique ability to do, like you'll see in Jonas's talk. But yeah, thank you for listening, and I will take any questions now.